Okay, this is our second video for section 13.4. We've been talking about motion, specifically position, velocity, acceleration, and speed. And now we're going to put that into an application which is known as centripetal force. So the word centripetal force, just kind of as a background, actually comes from the word centrum, which just means center, and piquer, which I think is French, which means to seek. So really what that is saying is to seek the center. That's what centripetal force basically is. So if we think about it in the terms of a circle, where maybe your motion goes in this direction, although the direction doesn't really matter, I don't think. What you have at every point on here is you have a velocity. If the motion is going around the circle, you have a velocity which is tangent to the circle. So it's going to go off like that. So that would be like your velocity. And then you're going to have an acceleration, which is going to be perpendicular to your velocity. And it is going to seek the center of the circular motion. So that is what is known as centripetal force. And what we're actually going to do here is prove an old equation that you are familiar with. So let's take a look at, yeah, I'll just keep the same color. Let's just say we have a circle. And we're going to say that our circle in general here is just going to be b cosine t, b sine t, 0, because there's no z here. We're just sitting on the xy plane. So we're going to call this our r of t. Okay, that's our motion. So the velocity is the derivative of that, which is going to be negative b sine t, b cosine t, 0. And then your acceleration is going to be the derivative of that, which is negative b, cosine t, negative b sine t, 0. So one thing that you should see here is the acceleration in this particular case is the same thing as the position function, but the negative. So the acceleration is really the negative of the position function, or the opposite of the position function. So a formula that you are familiar with is force equals mass is not a vector, mass times acceleration, where force and acceleration are both vectors. So one other way that we could write that would be to say that force is mass times the negative of position. Okay, exactly the same thing, because the acceleration and the position function are opposites. All right, kind of cool stuff there. Now let's actually put this together. And again, we're going to develop a formula that you may or may not have already seen, depending on if you've taken physics or not, for motion. So a very common thing that we deal with in physics is a projectile of some kind. So let's say we have a projectile which is launched from the origin, and whoops, that's supposed to be in blue. Launched from the origin, something like that. we should hopefully know that a projectile follows a parabolic arc. Excuse me. All right, so when you launch a projectile, you're going to have an initial velocity. Your velocity function, which would be a tangential function to the original curve, it will be a vector of some kind. It will create an angle with the ground. You're always going to have acceleration, which is pulling down on the projectile. At least here on Earth, you're going to have acceleration because that's going to be due to gravity. And then you're going to have a distance that the particle travels. So this right here would be your distance that the particle travels. Okay, so what we're going to do is I'm going to kind of take the initial velocity portion of it and I'm going to break it off into a triangle. So your initial velocity does something like this, okay, with the ground, and then of course you can make a triangle out here. So the initial velocity is going to have a magnitude associated with it, so we can just call that magnitude of the initial velocity, or v naught. We're also going to have an x distance and we're going to have a y distance associated with this. So one of the things we know is that the cosine of the angle is going to be the adjacent, which is x, over the hypotenuse, which is magnitude of initial velocity. Okay, if I want to solve that for x, which I can certainly do, I'm just going to multiply the initial velocity. So x is going to be, oops, let's write the initial velocity first. Magnitude of the velocity, cosine of alpha. Sine, going to be exactly the same idea. Let's use orange, I guess, for that. So sine of alpha is going to be the opposite, which is y, over initial velocity, or y is going to equal the magnitude of initial velocity, sine of alpha. Okay, we're going to need those pieces of information for what we're getting ready to develop. Okay, so all we know right now is that our vector for acceleration, let's go with blue. Our vector for acceleration, specifically at that very top point right there especially, has 0 x component. So it's not accelerating in either direction at the very peak there. But it does have negative 9.8 because of gravity pulling down on it. Okay, but we want to come up with a formula for the position of this function. So what we need to do is we need to work this backwards. I believe I left another page on here for you guys to write this on if you need to extend to go on to the second page, because I'm about to ready to run out of room. I'm going to keep extending my page instead of writing on the next page, but feel free to flip back and forth if you need to. All right, so the velocity function is going to be the antiderivative of acceleration. Antiderivative of 0 is just some c value, so we'll call it c1. Antiderivative of negative 9.8 is negative 9.8t plus another c value, c2. Okay, what we know is that our initial velocity, v of 0, is just going to be some c1, c2. And how do I know that? Well, excuse me, if I were to plug in 0 for all of the t's in my velocity function, all I would get out is c1, c2. Then my initial velocity before this thing is launched is going to be 0. Then after launch, it's going to have some kind of a actual velocity to it. All right, so what I know then is that v of 0 is going to be our initial velocity, which is going to be, let's see, the x component. I have to extend my page here. The x component is going to be the initial velocity magnitude cosine of alpha. Y component is the initial velocity's magnitude, sine of alpha. Okay. So if we want to find our actual v of t, because that's the initial velocity, that's the v of 0. V of t, because we've basically just found C1 and C2. This is C1, this is C2, is going to be initial velocity's magnitude cosine of alpha. Okay, nothing else there. And then negative 9.8 t plus C2, which is the initial velocity's magnitude sine of alpha. Okay, and that's a velocity vector for you. Okay, we're still trying to work back to a position vector, however. So we need to take an antiderivative of the position vector to get r of t. Okay, so let's do that. So the antiderivative of the x component is just going to be tacking on a t there, plus some kind of a constant. So initial velocity's magnitude cosine of alpha times t plus, we'll call it C3 in this case. And then the same thing here, except now we've actually got, let's see, negative 9.8 t. The antiderivative, that's going to be t squared. So negative 9.8 divided by 2 is negative 4.9 t squared plus magnitude of the initial velocity sine of alpha t plus C4, we'll call it. Okay, and now we need to figure out the C values. That one's probably the easiest one because the initial position of this thing, r at 0, is going to be at 0, 0. It started at the origin, which hopefully you can see on there. So that just means that 0 and 0 are your C values. So C3 equals 0, C4 equals 0, which means that r of t is going to be magnitude of the initial velocity cosine alpha times t, negative 4.9 t squared plus magnitude of the initial velocity sine of alpha t. And this is a formula that you may or may not have seen. Again, if you've taken physics or not, that's how you find the x component and the y component of your position of a projectile. So I'm going to go ahead and skip the blank page and just kind of rewrite this. The core idea was that x, or your x component, x of t, is once again magnitude of the initial velocity cosine of alpha times t. Y of t is the magnitude of the initial velocity sine of alpha times t, and then minus 4.9 t squared. These two things together make up your position, r of t. Okay, let's actually go ahead and do an example. Got a couple of examples actually. I think we can get these into this video. So for what value of alpha will d be maximized? Well, let's see. X of t is going to be our horizontal distance. And when we are talking about maximizing our horizontal distance of some kind of a projectile, which I will sketch on here for a second, we want the y value to be 0 because we want to figure out when it comes back down to the ground. So again, what we have, this is just a sketch. Whoops, that's supposed to be in black. Come on, work for me. There we go. So what we have is our projectile, which does something like that. We are talking about finding the distance or maximizing this distance d. We are going to have some kind of an initial velocity coming off of there. It's going to form some kind of an angle with the ground, which is alpha. So we are trying to maximize that distance, meaning we want to figure out the furthest distance this thing can have when it comes back down and hits the ground. So x of t is our distance, y of t is 0, because we want to know when it hits the ground. All right, so we know that 0 equals the y portion, which is going to be, now I'm going to go ahead and factor a t out of the y component. So it's magnitude of the initial velocity, sine of alpha, minus, now instead of writing this as the negative 4.9, I'm just going to write it as gravity divided by 2, so g over 2 times t. So when t equals 0, green here, t equals 0, what we have is, I'm sorry, not when t equals 0. T equals 0 is one of the solutions. We also take the other portion and set it equal to 0. And what I'm going to do is solve that one for t. So that means I'm going to add the g over 2t to both sides. And then we're going to multiply both sides by 2 over g, which is the reciprocal. So we're going to get that t equals 2 over g, magnitude of the initial velocity, sine of alpha. And I know that x of t, which is our distance, is going to be magnitude of the initial velocity cosine of alpha times t. But I'm going to replace the t. So normally we would have a t here, but I'm going to replace that t with this, because that is t. So it's 2 over g, magnitude of the initial velocity, sine of alpha. All right, so now we have to recall something. And this is why I wrote this as 2 over g. If you have 2 sine alpha, cosine alpha, all being multiplied together, recall that there's an identity which says that 2 sine of alpha cosine of alpha is the same thing as sine of 2 alpha. So we're going to replace everything that's circled in red with sine of 2 alpha. So x of t now is going to equal, now I've got 2 of those magnitude of initial velocities, so multiplied together, so it's going to be the magnitude of the initial velocity squared over g times the sine of 2 alpha. Okay, and why is that important? Well, I am trying to maximize this, okay? In order for me to maximize the position, the most that a sine function can be is 1. So we're going to have the maximum x distance when the sine portion is equal to 1, because everything else is just a constant. Whatever those are constants of some kind. So really what I need to do is I need to figure out, if I'm going to maximize this, the sine of 2 alpha has to equal 1. Anything less than that, it's not the maximum distance. So let's solve this for alpha. Well, then that means that 2 alpha, the angle, has to be, let's see, where is sine going to give us 1? Well, within a circle, it's going to be at pi halves. And then, obviously, we're going to try and figure out alpha, so we divide both sides by 2. So we get alpha to be pi fourths, which should make sense. A 45-degree angle of a projectile should maximize its distance. Probably something, again, if you've taken physics, you already knew all that. But the maximum x of t then is going to be, again, the sine part's going to equal 1, so I don't really have to write that. So it's just going to be the magnitude of the initial velocity squared divided by gravity. And that's how you'll find the maximum distance.